All right, so I'm still going to continue to play with trig functions a little bit. And I'm just going to play around here and have some fun, because calculus is fun for me. You guys are having fun some days. What I want to look at is the function sine of 2x. And a couple of things I could do about this right here is, I could try to take the derivative, which is what I want to do. I want to know what is f prime of x. Right? If I take the derivative with respect to x of the sine of 2x, what do I get? And first glance, I look at that and say, well, derivative of sine is cosine, so why isn't it just cosine of 2x? Well, let's test that out. So to test that out, I just make a graph and see. So let's get rid of a couple of graphs here. I find you can do lots of GeoGebras all at once, but if you had like 10 of them open, your computer's going to slow down a little bit. All right, so f of x equals the sine of 2x. All right, so there's my function, and I can see it's got a more rapid period than usual. The period is pi instead of 2 pi because of that 2 in front there. And I was wondering if the derivative function, let's call that d, like I've been doing for derivative, is equal to the cosine of 2x. All right, so I'm going to turn that off because I really don't want to see it, but I'm just going to check with a tangent line. So, maybe an easy place to check was what's the tangent at 0, because all I need is the slope there. So the slope m should be equal to just the derivative at 0. And okay, so this says it's 1. So the tangent line there should just be y equals 1x. Y equals x. Ooh, that's not it. Okay, so something went wrong. Having that 2 there made things more complicated. So I'm going to do this a different way. I'm going to apply a little algebra. So here's my algebra. Okay, so this, error, somewhere wrong. The sine, let's do blue, of 2x could also be written as the sine of x plus x. X plus x is 2x. And then I can use the angle sum formula to rewrite this. So angle sum for sine, so let me see, that is sine of the first angle times the cosine of the second angle plus cosine of the first angle times sine of the second angle. And let's see, I'm 90% sure that one's true. Actually, I'm 99% sure, but we'll double check in the trig formula since I got them out. Okay, sine of x plus y is sine of x cosine of y plus cosine of x sine of y. And my x and y are both x's, so I get sine of x cosine of x, cosine of x, sine of x. All right, so I got that right. And this cleans up nicely because these two terms are actually the same. So this is the same thing as twice sine of x times the cosine of x. And you may recognize this as a double angle formula, right, instead of the angle sum formula. Now this I know how to take the derivative of, so let's do it. So the derivative, let's switch to green. So f prime of x now can be done by taking of 2 sine of x, cosine of x. And 2 is a constant, so that just stays out front. And then I apply the product rule. And the product rule says take the derivative of the first function, derivative of sine is cosine, multiply by the second function. Plus, leave the first function alone, sine of x, multiply by the derivative of the second one. Derivative of cosine is negative sine. Use parentheses to be careful there. All right, so there's my rule. So that gives me 2 times the cosine squared of x minus the sine squared of x. And that looks familiar. Anybody recognize this right here? takers on that one? All right, let's go check our, I'm pretty sure I just saw that on that derivative, that trig cheat sheet here. Yeah, check it out. It's the double angle formula for cosine. Whoa. Cosine squared minus sine squared is cosine of 2x. So back here, I know that this thing right here is just the cosine of 2x, and then there's a 2 in front of it. So notice I missed that up here. I was just guessing it's 2x, but it turns out that 2 ends up jumping out front. Fascinating. Huh. Let's double check that to see if it actually works on the graph. Does that really give me the right slope? GeoGebra. So I was guessing this was the derivative here, which gave me a slope of 1 at the origin, and that was clearly not the slope of the wave at the origin. So now I think the derivative is 2 times that. And I think I have to reevaluate there. So that gives me a slope of 2. So the derivative should be at the origin, right? Y-intercept is 0, should just be 2x. Aha! Look it, we got that. There's the tangent at the origin. Okay, so let's check it at another place. Like if we just pick somewhere out here, like 1, like that point right there. Make sure it works everywhere, or at least 0 is kind of a dangerous place to check. So, because sometimes it's wishful thinking. So if I plug in 1, I want the point 1, f of 1. So right there on my graph, bing. And then the tangent line, using the point slope form, is just going to be y minus f of 1. That's the y value at that point, equals my slope, which I have a slope function up here. That's my d of x. So my slope is just d evaluated at 1, d of 1. And then times parentheses x minus x1, which is 1. And yeah, that looks pretty good, right? That looks tangent there. So this is just the point slope formula using my function and my slope function here. Slope function, y minus y1 equals m times x minus x1. Okay, oh, we got a question, let's see. Yes, so that's what I'm trying to get at. So Cole asked a good question. He says, is there a way to find this derivative without having to use this rewrite of the function? Because here, right, the sine of 2x looks simpler than the sine of x cosine of x. But it turns out with the derivative rules I have at the moment, I don't have a way to do that. So that's the next step. We need to find a way to do something like that. Because what if we can't rewrite it? Right, so let's take this one, for example. Suppose instead I said f of x is equal to the sine of x squared. I don't have a way to rewrite that, right? Look at all the trig identities. There is no identity that deals with the sine of a square. I can deal with sine squared, but notice the x isn't squared. That's different. This ain't the half angle formula. So nowhere here do I have a formula for something like the sine of x squared. So then you'd say, okay, well, how about if we rewrite that? That would be the sine of x times x. So is there a formula for something like the sine of alpha times beta, the product of two angles? And I don't recall such a formula. So what we want to do is what if we can't rewrite this? How do we take the derivative with that there? Because what we're going to find is if we try to claim that it's easier than it is, that f prime of x, derivative of the sine is the cosine of x squared, if we check that out, just like before, this is going to fail. This is more complicated. And we could graph a tangent line to see that that doesn't work. So what the heck do we do? All right, so I'm just going to do kind of a little algebraic jiggery-pokery here. And this is based on an idea I talked about the other day, a couple times, when I was playing around with what does h look like on the graph compared to dy dx. And so just a reminder about where derivatives come from. F prime of x is equal to the limit as h goes to 0 of f of x plus h minus f of x. This is the derivative. This is where they come from. Without this, we got nothing. Sometimes instead of a h, we call it delta x for a change in x, because that's what h is. It's a change in x. So often instead, we might see the limit as delta x goes to 0 of f of x plus delta x. So all I'm doing is swapping the h out for delta x here over delta x. Now, delta x is a change in x. This numerator is just a change in y. So summarizing this further, a shorthand for this is the limit as the change in x goes to 0 of the change in y divided by change in x. And basically this says, hey, find a secant, let the change in x get smaller and smaller, watch what happens to the change in y. Do you see a pattern? We call that pattern dy dx. And so that dx, the delta x turns into a dx, the delta y turns into a dy. And these dy's and dx's are referred to as differentials. And the early people that developed calculus realized that this limit process is kind of sketchy, but super powerful. And so some of them said, like this dx and this dy thing here, what they are is infinitely small changes in x and y. So we're saying take the limit as x goes to 0, but we can't actually get to 0, otherwise all of this falls apart. So these numbers aren't 0, but they're as close to 0 as you could ever get. And you might ask, what does that mean? And that's a little weird. We're not going to get to that philosophical thing. We're just going to say, hey, these guys are just tiny little numbers, the tiniest numbers in existence. Kind of like subatomic particles is one way to think about them. So if I have something like the derivative of this function f of x with respect to x, and I claim it equals to this other function that we call f prime of x, the dx I can actually treat as a number, and I can multiply it to the other side. So that means the derivative of my f of x could be written as f prime of x times this tiny little number dx. Now the derivative of f, that's really dy. So in other words, I'm saying this tiny little change in y is proportional by this function to this tiny little change in x. So if somebody gives me a small change in x, I know the slope to convert to a change in y. So that's another way to think about it. And this version of a derivative is called the differential form of the derivative. And it turns out it's super powerful. Differential form of the derivative. Derivative. Ooh, that did not come out right. Derivative. There we go. Sometimes I have trouble getting letters in the right order. Slightly dyslexic. All right, now some of you are probably going to go on and take a lot more math, and you've maybe been looking ahead at math classes you might take in the near future. And there's a famous math class called Differential Equations, which is super awesome, beautiful stuff. It's awesome. And so this is related to that. It is an important idea that I can actually separate the dy from the dx. And like here, when I write it like that, it's one thing. It's that thing, whatever that function is. But it turns out they are separable. And this is important. Why? Well, let's take a look. That function I was looking at earlier was y equals the sine of 2x. And really, this is the composition of two functions. So I could say this is f of x equals the sine of x composed with g of x equals 2x. And so that composition, y equals f of g of x, is the sine of 2x, right? A function within a function. So I'm just going to kind of break it down that way. And I'm just going to rename things a little bit. I'm just going to call, instead of using a y, I'm just going to use a g and say g is 2x. And then I can take the derivative of g with respect to x. And so the derivative of 2x is 2. And then I can rewrite that in differential form. So this says dg is equal to 2 dx. So that's the differential form. Next, let's look at the sine of x. So sine of x, I'm just going to call that y like I did above. So y equals the sine, but this time instead of calling it x, I'm going to call it the sine of g. Then the derivative would be dy dg. And a derivative is just a change in the dependent variable divided by a change in the independent variable. So since I'm using a g instead of an x, the g goes down there. And what is the derivative of the sine? It is the cosine. Since this g matches that g, it's just the cosine of g. And if I rewrite this in differential form, this says dy is equal to the cosine of g times dg. But up here, we know that g could be written as 2x. And if that's true, then dg is 2x dx. So now I'm going to just put this information in here. So that goes there, this goes there. So what do we get when we use this differential form? We get the cosine of g. G is really 2x. And then dg is really 2 dx. Okay. So putting that together, based on this function right here, and that differential magic I just pulled here, I know that dy equals the cosine of 2x times 2 dx, but I'm just going to divide that dx to the other side. Right? So I take this dx, I divide it over to the other side, I get dy dx is cosine of 2x times 2, which is what we discovered before, which is kind of magic. So what happened here? Here's the summary. This is called the chain rule for calculus. And what the chain rule tells us is how to take derivatives of composite functions. So how to take derivatives. Oops, and I am out of time. Oh my gosh, how did that happen? I was having too much fun. That's okay, we're a day ahead. Almost half a day. Real quick here. If you have the derivative, and I'll do more work to prove this next class, of a function within a function, what ended up happening back here is we had an outer function and an inner function, right? The outer was the sine of x, the inner was the 2x. So the rule is take the derivative of the outer function as it was, don't mess with the inside. Then multiply by the derivative of the inner function. So the chain rule just says, hey, you've got multiple derivatives, they're connected together. It's just the outer derivative times the inner derivative is the chain rule. So I'll do more to justify this next class instead of just that one example, but the one key to justifying this is the idea of these dx's and dy's as a differential. All right, that's it for now. Thanks for playing.